right, well, I'm Nick Solomey, professor of physics here at Wichita State University, and I'm going to be talking about space radiation, and we'll also have a lab associated with this with a hands-on project tomorrow, and I'll bring in some equipment from my lab. Formally, I'm not a person who has ever in the past worked for NASA until just recently. Technically, I'm trained as a particle physicist working at CERN in Geneva, Switzerland, and Fermilab in Chicago. And but there's many different types of physicists, not just the kind I am with a particle physics. There's nuclear physicists, and then elementary particle physics, which I do. But there's also atomic, molecular, and optical physicists, and there's a solid state physicists who deal with the structure of matter and its properties and how to make things like superconductivity. But there's quantum physicists that deal with the quantum mechanics effect, gravitational physicists, and astrophysicists. That's a catch-all for anything that's done in space. And biophysicists, or sometimes called medical physics or bioengineering, depends what name you want to attach to it. So all of these people, although these are different branches of physics, all of these types of physics people actually would have a role in many different aspects of NASA. What does NASA do? NASA does a lot of things. Science studies in space. They have divisions dedicated to specific objects. Studying the sun and its core would be part of like NASA's heliophysics division. Cosmic ray, gamma ray observatories is something NASA just launched the Fermi spacecraft, which was, of course, its predecessor was the EGRET, energetic gamma ray spacecraft. And we have spectroscopy for planet studies, and we have sensors for observatories in space. Quantum communications is a hot thing right now. NASA's trying to dump an extra 10 million a year into mostly because the Chinese are doing it. But it was known that you could do encrypted messages with quantum communications. Black holes, neutron stars, active galactic nuclei, these are all very important aspects of the larger cosmology. And then life on other planets or exoplanets, even imaging exoplanets is a new goal of NASA. So what I'm trying to say here is that even though you might be studying one small branch of in engineering or one small branch of science, what I'm trying to say here is that it could play a very important role in a program such as NASA's program. So specifically, though, the NASA Space Science Division, this is the division that actually tries to do space science. It's also called the Space Science Mission Directorate, SSMD, as opposed to Space Science Technology Directorate, which deals with like developments of rockets and habitats and things like that. But the science division is pretty much these 5 divisions: heliophysics, dedicated to study the sun and space weather; astrophysics, which studies stars, galaxies, the universe, cosmology, dark matter; astrobiology, life's origin and elsewhere in the universe. So life origin could imply here on Earth. There's a lot of interesting aspects of astrobiology that are exciting. Like there's no smoking gun of where life actually originated here on Earth. But no one's willing to say, let's just assume it came to Earth from someplace else, because that takes the point of how it developed and pushes it somewhere else where you can't study it. So people don't like that aspect of it. The Earth Science Division, that means you're going to study the Earth from space. And then the Planetary Science Division, such as studies of the planets and exoplanets. So you can see it's a broad topic of NASA Space Science Mission Directorate. But these are all the 5 mission directorates of the NASA sciences. So the aspect I wanted to talk to you today about is something about essentially how I relate to the world of NASA. And in a lot of ways, it has a long history that goes back a long ways. Radiation in space. So, well, radiation is actually discovered in 1895, and I was just noticing on the wall here, that's the actual year that the Fairmount College was founded. So, of course, radiation in space comes with the same exact year as us founding the Fairmount College here in Wichita. The people who discover radiation are an interesting group of people. It's the Curies, Marie and Pierre Curies, as well as Becquerel. And they do it quite accidentally. They had a drawer full of photographic plates, and in another drawer above it, they had some rocks. And I'm going to bring in some of these rocks tomorrow for our hands-on lab. And these are rocks that are commonly found here in Kansas, but they had gotten them from Africa and not Europe. And it turns out that those rocks made the photographic plates exposed, even though those plates were never exposed to light. And that's the discovery of radiation. We want to talk about, how do you protect yourself from radiation? Well, first of all, you're going to find out over the course of today and tomorrow that space radiation is all around us. There's space radiation coming from deep space. There's radiation coming from the inside of the Earth outwards. We make it. You could be hiking, or I was hiking in Kansas. So what's the name of that place in Kansas where you have it looks like these castle rocks? You drive out very far west and you go south. Castle Rock. Yeah, I think it's Castle Rock. And I was just climbing there with my children, and I was stepping on a rock as a part of a ledge to go up on, and it broke off. And it broke off, leaving behind these very bright yellow dots. It's like, wow, that's a weird rock. Put it in a bag and took it home with me. It's not a national park or a state park. It's a private property, actually, Castle Rock. But people are aware of that. So anyway, it's a rock that's has uranium in it and a little bit of plutonium, although it's small amounts of plutonium, but we can see it in my lab. But how do you protect yourself from radiation? Well, you're going to limit your time exposed to it. So if you're exposed to it for a minute instead of 10 minutes, you have 10 times less dose. You can increase your distance from it such that the radiation is going to fall off as 1 over r squared. So doubling your distance means the radiation is 1/4 the strength. And you can shield yourself by putting material between you and the radiation, such as concrete, water, atmosphere of our planet. And the fourth way you can protect yourself from radiation is a magnetic field. Not all radiation is neutral. A lot of radiation is charged particles like positive charge and negative particles, like electrons. And a magnetic field is going to actually sweep away those particles so it won't reach you. And these are the ways in which you can protect yourself. Cosmic radiation, the Curies and Becquerel discovered radiation, and people start to wonder, where is this radiation from? And yes, originally it was discovered to be from rocks that they just had in their lab. And other people, Professor Hess in Germany, goes from 1895 to a 1913 study. He's measuring radiation in his lab, which has nothing to do with rocks. He's just measuring radiation, which turns out to be cosmic radiation from deep space. And so he takes, by the way, for those of you who don't remember, when was the hot air balloon invented? 1900. 1890. It's about the same time as the discovery of radiation. So Professor Hess, Victor Hess is his name, arranges to have the use of a hot air balloon. And he's going to take this hot air balloon up into the atmosphere, and he's going to measure in both 1913 and 1914 radiation that's falling on his detector. And he notices that as he goes up higher, not at first, but as he goes up higher, the radiation is going to increase to over, let's see, almost 4 times what you see down here at on the plains of Europe and Germany. And so he's going to go up almost a little bit more than 4 times the radiation as he goes up to what's the altitude he gets up to? He gets up to 12,000, 14,000 feet in this balloon. and then he comes back down. He's done this several times. So, so it's radiation that is going up as you go higher and higher into the atmosphere. So it's an interesting aspect. Now, I actually had mentioned this to one of my group of students. Oh, this was like 9 years ago. And they had the idea to take my Geiger counter and a backup battery from the computer, because the backup battery could provide an AC power source. And they drove to Pikes Peak. How high is Pikes Peak? Yeah, 14,000 feet almost. And has lots of places to stop and make measurements along the way. There's lots of car parking spots. So they took the Geiger counter in the lab without it, because they're not allowed to take a radioactive source with them, because that's against DOT laws to transport radioactive sources. In your car, at least. You could ship them by FedEx if you declare them to be radioactive, but you can't take them in your car. But they were just interested in measuring cosmic rays. So they took the Geiger counter and took it up Pikes Peak, and they had a very similar curve. And it's just all, they didn't need a hot air balloon. They just, well, Pikes Peak is a road that goes up the peak. And it's, for those of you who've ever been there, you know, it's quite a drive up, right? And it's quite a drive, even scarier drive down.
Only with the 30-foot motor.
But you can see the same exact curve, except for in one spot. In one spot in Pikes Peak, the rate's going to go up about a factor of like 100. And it's not because of the radiation from space. It's because one of the parking lots is sitting next to a layer of rock in the geological record, which is radioactive, very radioactive. And so that's what caused it. So if you throw that one parking spot out, it just follows Hess's curve perfectly. So you don't need a hot air balloon. You could do it by just going on a road, a tourist road to climb. So what is cosmic radiation from deep space? Well, cosmic radiation from deep space is two basic types. There's these high energy gamma rays and high energy protons. That's the bulk of it. And they actually produce showers in the air very different from each other. High energy gamma rays coming from deep space will hit the upper atmosphere in the material, and they're going to make electron-positron pairs. Those electron-positron pairs will scatter and make other photons and electron-positrons again. And so you're seeing mostly showers, we call them air showers, that are mostly just photons and electrons or positrons. Another type is protons, or actually anything else. 1% of the time, it's not protons of the charged particles. Sometimes it's helium nuclides or iron nuclides that are accelerated to very high energies, and they hit our upper atmosphere. And those showers are very different. They produce lots of photons, just like but they're going to produce pions, muons, and neutrinos, as well as the photons and pretty much not much electrons. So you got two different major types of particles from cosmic radiation hitting our upper atmosphere, and these radiation then make air showers, because the Earth's atmosphere is about 60 miles thick, and it's the equivalent of about a half a mile of water. That's the protectiveness, if you want to compare it to water depth. Because the atmosphere, the pressure drops off as you go higher. So even though we call it 60 miles of atmosphere, the pressure, it's becoming less and less dense as you go higher up.
So the reason it's higher when it's higher up is because it has to split off.
Well, yeah, there's a chance it'll have less interactions, and as you go deeper, the chances are you're becoming lower energy, and in fact, you're going to hit more atmosphere. And so there's two effects that make it develop a shower as you become deeper. A, the atmosphere is becoming denser, and B, the primary particles become now half the energy, having shared it between half electron. So every one of these you could be looking at it as the division of that energy is split into two, that's split into two. And as you know from that mathematical progression, you lose energy very fast. And actually, you're going to find that maximum, what we call air shower maximum, charged particle density is actually not here on the surface of the Earth. It's about 800 meters above the surface of the Earth is where the maximum air shower is. Now, of course, 800 meters, we'll get to that. What's the problem here in Kansas? We're not at sea level. We're at 1,300 feet. And what's Denver, Colorado? Mile High City. So it's at 5,600 feet. So you're measuring different depths of the air shower in there. So one of the first things that we did just after the birth of the space age, don't forget that Sputnik's being launched, what, in 1956? Jim would probably have those numbers memorized, but this is very early in the space age. 57, yeah. Of course, these numbers are not completely correct because the US had intercontinental ballistic missiles sitting there fully loaded for that, ready to go. It's just, it wasn't the official start of the space age. And of course, the military had tested their rockets long before we created NASA and started doing space exploration or putting things in orbit. They had been testing these suborbital flights. So they've existed.
Eisenhower really loved missiles and rockets.
Oh yeah, Eisenhower liked missiles, that's right. And you're gonna see, well, this is the first, one of the first rockets that are gonna put a spacecraft to actually do scientific missions into space. And it's called the Explorer 1. It's in 1958, and it's gonna be a successful spacecraft that's gonna orbit the Earth. And it's gonna create a very unexpected discovery. And this unexpected discovery was made by Van Allen, working with NASA, but not for NASA, through a University of Iowa grant, and it launches the Juno 1 rocket. And the Juno 1 rocket, by the way, you might call it a Redstone rocket. It's just a copy. It is actually just the intercontinental ballistic missile of the US program. And we've had intercontinental ballistic missiles from the 50s, early 50s. So these rockets did exist. We just took them from the military aspect where you deny that they exist and you move them to where they, you admit that they exist. So Van Allen took took a spacecraft instrument and he puts on board this spacecraft instrument a cosmic ray package. The cosmic ray package is going to measure radiation as it goes up into space. And this rocket then goes up into space and it launches through several layers of the Earth's radiation belts. And he discovers the Van Allen radiation belts, named in honor of him. And you can see this from the track that the spacecraft took here in blue. As the spacecraft goes away from Earth, it goes through these various radiation belts where he's actually making measurements. It eventually goes way out and comes back in again close to the surface of the Earth. And it just keeps on going in an orbit that is low Earth orbit all the way out to very far away. Today we would refer to this as a GTO orbit, geotransfer orbit. And the flight path is in blue, and it's the first map of radiation around the Earth. And he discovers several layers of radiation belts around the Earth. These turn out to be protective radiation belts where the Earth's magnetic field has trapped large amounts of radiation so it can't reach the Earth. And it's a protective layer that surrounds the Earth. And here's just a picture of his measurement using this Explorer 1 spacecraft and the first proof that the radiation belts exist. So the radiation belts, some people call it 2 layers of radiation belts. Other people call it 3 layers of radiation belts because the outer radiation belt does have 2 peaks in it. So the spacecraft in low Earth orbits don't actually have to worry that much about always passing through the radiation belts, except for something called the South Atlantic anomaly, which we'll talk about in a few slides. But it's essentially 2 layers of intense radiation that protects the Earth from the cosmic radiation. And it's our major, it's a major problem for operating spacecrafts or humans flying in space because they can get exposed to a lot of radiation. So there is something weird though called the South Atlantic anomaly. And the South Atlantic anomaly is over the South Atlantic Ocean and a little bit over Argentina. But it's in the very far south of Argentina. If anyone knows where Mendoza is in Argentina, well, you teach Spanish, you might know where Mendoza is. It's very far south. And even then, you would actually, so on a map here, it's way down. Okay. So the South Atlantic anomaly is really unusual because it's an unusual effect because the Earth has a center that we rotate around in green. But that center is not the origin of the magnetic field of the Earth. The magnetic field of the Earth is molten iron that is charged that's moving inside the Earth's core. But it doesn't circle around the center of our geometric center of the Earth. It's actually centered around its own little spot. And that's slightly shifted in location away from the South Atlantic anomaly, which means that now the magnetic field that's protecting the Earth is actually touching in the South Atlantic. So the Van Allen belts actually touch the Earth in the South Atlantic anomaly, creating a huge amount of excess radiation on the surface of the Earth in that one specific spot. And it's called the South Atlantic anomaly. And one of my colleagues at NASA Marshall Space Flight Center has a science package on the International Space Station called the neutron detector. And this is a graph from his actual data where the International Space Station is in low Earth orbit. And that low Earth orbit, every orbit he's measuring neutrons in his detector, and every other orbit is a little higher than that. And every 10th orbit, they actually go through the South Atlantic anomaly. And you see that the radiation count goes from this nominal 500 up to this 5,000. So, and for a brief period of time, the International Space Station is exposed, 10 times the amount of radiation, because you're actually going right through the South Atlantic anomaly where it touches the surface of the Earth due to the fact that the magnetic field of the Earth, and don't forget, I said one way to protect yourself from radiation is to use a large magnetic field to sweep away the charged particles from reaching you. And here you have that now if you're in space, such as on the International Space Station, which is a low Earth orbit, the International Space Station is always like 150 to 250 miles above the surface of the Earth. And
when you say a short period of time, are we talking minutes or hours? Because I know it only takes the space station 90 minutes to go around the Earth.
every peak here is 90 minutes. So you can see that that width is about, what, 15 minutes wide? But there's other ones when you get kind of close to the South Atlantic anomaly. But about every 12th orbit, you go right through it. And there's a few orbits where you're close to it. And it's radiation. No matter what you do, you have to be prepared for living with radiation in space. And of course, the space station might have other ways in which you could shield an astronaut. There's also ways that there's nothing you can do but to be exposed to it for a short amount of time. Deep space, the problem becomes a little bit more complicated and worse. We talk about here on Earth, taking balloons up. We fly up to 14,000 feet, or you can drive up the Pikes Peak, and you saw that it was 4 times more radiation. You see that the International Space Station, when it goes through the South Atlantic anomaly, every now and then has 100 times, or no, it was 10 times, 500 to 5,000, is 10 times more radiation for a short amount of time. If you live in Denver, Colorado, you have to be prepared to live with 4 times more radiation than, say, someone at sea level. And as you know, we're not at sea level. We're at 1/4 of a mile above sea level. So our radiation level is also higher than, say, someone that's on sea level. But we're not as bad as people at Denver. So we saw that low Earth orbit, you have to be prepared to live with radiation. And out to higher Earth orbits, space is a very harsh environment. radiation of this nature actually destroys equipment fairly quickly. Your computer, that's this laptop, or your cell phone will not last very long in deep space. You would be, unless you make it out of something called rad hard silicon, which is really expensive. And so this equipment that we hear here on Earth is not certified to fly in space because it's not made out of rad hard silicon. Neither is your cell phone, by the way. But however, this harsh Earth orbit, we need to find a way to manage and design equipment to operate it. And this designing equipment has been achieved because there's some equipment out there in space that has been operating for more than 50 years and is still working and it's still doing a pretty good job. Some of the equipment we left on the moon is still actually working. Not all of it, but some of it is. The batteries were dead actually on the little rover that they had for the astronauts to ride around on practically the day before they left because they overheated in the sunlight, but not due to radiation. But there's equipment that's flying out there, the equipment on the moon. There's some spacecraft that are still orbiting the Earth made out of original late 1950 electronics that's still responding and sending out a signal. But there's geostationary satellites. You don't want to have to keep putting a geostationary satellite up into Earth orbit every single year to replace the one that's up there. Because then the space is going to get really crowded really quickly. And these things, they try to design them so they'll last 20 or 30 years. Although I think the last, China had launched for some South American country a telecommunication satellite that was supposed to last for 20 years and it operated only 4 years before it died. So that's a problem. You got to be careful what you put. So let's turn our attention next away from the Earth and start looking at deep space and beyond Earth, which includes the moon, Mars, and travels to the distant planets. Voyager 1 and Voyager 2 are the two objects that actually are the furthest from the sun. Well, that are at least still responding. No, I think actually that's not true. I think Pioneer 10 and Pioneer 11 actually were passed by Voyager 1 and 2 in distance from because they were going slower. But just 20 years after the first satellite was launched, we launched two space probes to the outer planets, Voyager 1 and Voyager 2. And they would visit up close Jupiter and Saturn. And I remember when I was in college, it was exciting to see this data coming in. It was a lot learned. But these spacecraft were launched in September and August of 1977, with the first one being launched in August was called Voyager 2, and the second one being launched was called Voyager 1. That's because one would pass the other very quickly, and they both went to Jupiter. They both went to Saturn, but then Voyager 1 goes turning off into deep space away from the black solar plane, and Voyager 2 goes on to Uranus and then Neptune. And so these are part of the great exploration. And there's a lot of fun things that we did. We were able to look at Jupiter's great red spot, a hurricane that persists for hundreds of years on the planet. We were able to study Saturn's rings when viewed up close to see it has a lot of substructure of individual particle matter in motion. We're able to see the polar region around Uranus, and we were able to see on Neptune, which is an ice giant of a similar structure to Jupiter, but much colder. It too had a hurricane storm that persists for hundreds of years. It's not a big red spot, it's a big blue spot. So we saw a lot of things in that sense. But one thing that the Voyager spacecraft took with it was a radiation monitor. It actually took two radiation monitors that are identical. One radiation monitor is just a tube, like the kind you'll use tomorrow in the lab that I have planned here. And the other one is that same identical tube, but it's encased in a piece of iron. So that one will just measure anything, and the other one will measure only things that are above what's called 70 million electron volts, that could get into that piece of iron. And so one's called a high energy detector. The other one's called a low energy detector. Although the low energy detector does detect high energy as well. It's just that it's called a low energy detector. And you'll see that, on one end of the spacecraft, you'll see that there's the radioactive sources that power the spacecraft's energy. And as far away from that as the cosmic ray monitors. And these cosmic ray monitors, the low energy and the high energy, this is data from, what day was this? I think this was just taken 2 or 3 weeks ago. A snapshot of the live image from JPL's webpage shows that the spacecraft's been traveling for 43 years from the launch date. The distance from the sun is 152 and 127 times the distance the Earth is from the sun, called an astronomical unit. And our radiation monitor, where you're seeing mostly it's high energy stuff and very little low energy stuff. When we first launched this probe into deep space, when we left the Earth, we noticed that the high energy stuff was very low and the low energy stuff was very high. And it's now reversed. And the reason for that is that the Voyager probes, as they traveled away from the Earth, the radiation levels have increased. So there's less protection from the sun as you went away from the sun. And that's a very important point, because as you travel away from the Earth, the radiation levels increase. There's the increasing of the two monitors, and sometimes there's some big jumps as you, I didn't go all the way back to 1977 because this graph would be harder to see, but around the year 2010 or 2009, and another one in about the year 2011, you see some jumps in these monitors at the energy, the rate of these counts per second increasing. And it's a 5-day running average that they took here to make it a little bit smoother. And the energy had to be greater than 288 protons is what they said in this analysis. And these are some sudden increases, and there's a change in the radiation levels. So the question is now, what happens if you go further out? And here's the Voyager's evidence that we're inside the Earth and we're protected. Then we're orbiting the Earth and we have higher radiation, but we're still being protected by the sun's magnetic field. As we go away from the sun's magnetic field becomes less, and we get less protection from that. And as we go very far away, in 2018, we noticed that the galactic cosmic ray rate really shoots up, and then the particles from the sun really go down. And this is the proof that this spacecraft has left the protective layer of our sun called the heliopause. And this is a very interesting structure. On the left here is the Earth. The Earth is a round ball. It has an intense magnetic field. There's this radiation that we call solar wind coming from the sun, and it gets smeared around so it doesn't reach the Earth. And it's protecting us. Well, the same is true here with the sun. Here's our sun. Our sun is orbiting around the galactic core. There's huge amounts of radiation coming from this galactic core. And we have something called the heliopause, which is very similar to the bow shock of the Earth, protecting us from our own sun, as the sun is protecting us from the galactic radiation from the core of our galaxy. And Voyager probes are believed now to have actually left the heliopause in 2018. So just a little while ago. I think that's, and the date, the actual date is debated, of course, but most scientists take it as 2018 for the date that it left. Okay, so here's a description of how the sun is protecting us. And by the way, oh, you are here. So if this is our galaxy, of course, this isn't the viewed, it is data, but but it's not real viewing. It's taking the known location of everything from us and then saying, what would this look like if we were sitting out there at like Andromeda Galaxy and looking back at us? And this, then we render rendering of using all the known data. And we are here in what's called the Orion Arm. And the radiation from the galactic core is immense. It's 700 times higher energy compared to what's coming from our sun. Yet we still have a protection from this intergalactic space radiation, which is even worse. The sun takes about 150,000 years to go around the galactic core. And it's a very interesting thing because how often are these great extinctions on our planet? Every million years or so. So, so we go around the galactic core 10 times and we get an event that could destroy the life on the planet. Okay, so the point I'm trying to make here is though that it's a huge combination of things. The Earth, of course, has we live on the surface of the rocks or on the very top surface of the water for a lot of the sea creatures. The Earth has a magnetic field that's protecting us. The sun produces a magnetic field that even adds more protection from the stuff coming from the galactic core and from deep space, so it can't reach us as easily. But imagine you're actually now going to another planet. The Earth is protected, but Mars or the moon is not. Mars has no magnetic field. Our moon has no magnetic field. And so there's also no atmosphere on the moon. There's a very bad joke. Someone told me at NASA, an astronaut went to the moon. They came back, they said it was a great restaurant, but it had no atmosphere. Anyway, the moon and Mars are both in the Goldilocks zones, as well as our Earth, distance from the sun. But without a magnetic field, there's no way life could ever exist here because there's no protection. And so you saw the Earth, you had all these bow shock waves. Now you see Mars, and it's just exposed directly to the solar wind. It's destroyed very quickly. Any life there. Now, of course, you could still live on Mars if you go underground, because you could, instead of having a magnetic field, you could increase the amount of mass you have over you. And you could sleep underground, which isn't that different than what you do on the space station, where you have different compartments with different amounts of radiation protection. So the moon and Mars, a lot of people say they want to go and colonize it, they want to go and live there, but you got some major problems here. You have no protection at all. The atmosphere of Mars. Going close to the sun is the other direction. The going close to the sun has a nice feature. You're going close to the sun and you can increase the magnetic field. So you'll have some extra protection from galactic cosmic radiation from deep space. But as you don't forget what I also said about radiation. It goes as 1 over r squared. So if you go 2 times closer to the sun, you actually increase your radiation from the sun by a factor of 4. And so low energy particles from the sun are going to go up. High energy particles are going to go down because of the magnetic shielding. So NASA created in 1974 in cooperation with Germany, Helios 1 and Helios 2 spacecraft, and it would go within 35 solar radii of the sun to study the sun. And we measured on this experiment radiation from the sun, and there's 2 different modes, what's called shock and continuous. The left is prompt and shock, and the one on the right is pretty much a continuous spectrum. And you can see that the radiation stops at about 100 MeV, 200 MeV of protons, and stops at about 10 MeV of electrons. So those are actually very low energy particles that are relatively easy to stop with shielding. The sun itself, like I said, has this huge magnetic field strength, but the sun is not a sphere, the solid sphere like the Earth is. The sun is a gas. And so as it rotates, the center is going to rotate faster than the polar regions, and it quickly distorts all the field lines that are present. And we end up also with the fact that the sun will have sunspots, which are intense magnetic field regions of north and south poles that come back, and they generate magnetic field loops. And these magnetic field loops are really nice because if you ever take your sunglasses, like for the solar eclipse, and go look at the sun right now, you'll see one big prominence and a couple sunspots. I don't know if Jill has any left over from the solar eclipse. You know, so I think I could find one in my glove compartment of my car. I could show tomorrow. But the sun right now has some very nice prominences and the sunspots. And the first solar flare was observed in, what year was this? 1859, long before radiation was discovered. And they didn't know what they were looking at. But Richard Carrington in England saw an event where he was studying a sunspot. And while studying that sunspot, he saw a bright flash of light move across the surface of the sun. And this was a solar flare, a prominence. And what these prominences are is they release all this matter into space. And the sun is releasing matter into space. It's called coronal mass ejections all the time. Flares and prominences from the sun, there's a nice picture of one, get released all the time, and they go out in all directions. Now, of course, all the planets sit on a plane, and of course, Earth is a little tiny speck. So it's really hard to be hit by one of these. But this 1959 solar flare observation was probably the world's largest prominence ever seen. And it has some interesting outcomes. The damage from the coronal mass ejection. So that 1859 event where the mass from the sun was ejected and it came directly towards and hit the Earth. I mean, what were we using in 1959? Candles, horse-drawn buggies. There's no cell phones, no laptops, no computers, no electricity even, no generators, and definitely no electric motors. I mean, Tesla doesn't invent the electric motor until the 1890s. So there wasn't much going on the Earth, but the Aurora Borealis was seen down in Cuba that year from this prominence. That's never happened before. We have not seen that happen since. So Lloyd's of London got together with Forbes magazine and got together with the US Solar Observatory in Hawaii. And they worked out to figure out in 2018, what would be the damage to our society from a coronal mass ejection like the 1859 one that hit the Earth. And they concluded it would be $2.6 trillion of damage. That's 25% of the economy, or 15% of the economy. It would be damaged if we had such a coronal mass ejection today. The second biggest event ever recorded was 1921, coronal mass ejection. That would have been $0.4 trillion, much less. And 2 weeks after Apollo 12 landed on the moon, a small coronal mass ejection hit the Earth and it hit the moon. It would have been enough to have killed the astronauts in that Apollo 12 mission on the moon. But NASA did have a plan. It's a really interesting plan. I don't know if it'll work, but the plan was if a coronal mass ejection was coming towards the moon while people were walking on the moon, the two astronauts were supposed to crawl underneath the lunar lander. One was supposed to lay on top of the other, and then every 15 minutes they're supposed to change the location of who's on top and try to reduce the radiation amount of time by protecting the other. So that would have given them half the radiation exposure. And because they're underneath the lunar lander, they would have also had a little bit of mass above them for protection. But NASA never actually ever had to implement that plan, but they missed only by 2 weeks for coronal mass ejection. So the solar wind, as we learned, is a very massive thing. The solar wind produces particles from the surface of the sun, electrons and positrons, and some small amount of protons, which come to the Earth. It gets funneled down to the polar regions. It makes the aurora borealis that we see. If you've never seen the aurora borealis, go to the Upper Peninsula of Michigan, or go to the border of Canada and Minnesota. Those things are beautiful places in October and November to see the aurora borealis. One of the instruments still working on the landers is the solar charged particle measuring devices that they left on the moon. And so we actually could see a lot of solar radiation from our sun, which, like I said, it only goes up to 10 MeV electrons and up to 100 MeV protons. It's nothing compared to the energy of particles that are hitting the Earth from deep space. It's nothing compared to the amount of energy currently being hit by Voyager 1 and 2, which has left the heliopause. I give you a depiction here of galactic cosmic radiation in 3 situations. One is the situation where we are very far away from the sun. Then we get closer to the sun, and then we get really close to the sun. And as we get really close to the sun, the low energy particles are starting to vanish as we as a function of energy. And the only thing making it to close to the sun is actually very energetic particles. Low energy particles from deep space of the 1 GeV are starting to be reduced by the sun's magnetic field. So anyway, the Earth is a great, and our sun is a great way to protect us. It's assumed, by the way, that even our galactic core is protecting us from radiations from outside their galaxy, such as quasars that are blowing up at very far distances. But in addition to that, the particles that are hitting the upper atmosphere of the Earth could actually be used for science studies as well. And one of these science studies is called the High Energy Gamma Ray Observatory. This first one was 1992. NASA launched the Egret Observatory. So the Egret Observatory is a great little spacecraft. Launched in 1992. First time NASA's going to try to do high energy gamma ray astronomy in space. Before this, maybe there was some high energy gamma ray astronomy being done in space already by the Defense Department, because we know in 1978 that a Defense Department satellite spotted a very large gamma ray burst in the South Atlantic Ocean off the coast of South Africa, which we are almost 100% certain that was Israel cooperating with Taiwan, cooperating with South Africa to do a nuclear test explosion. And it was seen as a gamma ray burst. And so hence we know, even though all 3 of those countries deny it, we know that both Taiwan, Israel, and South Africa have nuclear bombs, because they were all 3 involved in that test from the boats that were present around the explosion area where we saw the gamma ray burst. So these are problems, but this observatory is a stack of spark chambers. And then we saw gamma rays come in, hit the target, that produced 2 electrons. And we took the data, and we, after several years of mapping, we see Egret's all-sky map of photons above 100 MeV. You can see the galactic core. You could see the Ganymede and Crab pulsars over here. You can see a few other sources that they didn't even know were sources. And we opened up a whole new way of looking at the universe called High Energy Gamma Ray Observatory. Then after Egret operated for 8 years, NASA launched the Compton Gamma Ray Observatory, and then it was replaced by the Fermi Gamma Ray Observatory, which is still operating today, doing high energy gamma ray. The other thing we could do from cosmic radiation in deep space is to try to measure cosmic rays. Now, cosmic rays are charged particles from deep space. And as I said, charged particles get swept by the magnetic fields, and they don't actually point back to where they came from always. But as you get higher and higher energy, you actually bend the charged particles less and less. And we'll see this tomorrow in tomorrow's lab, where we talk about radiation, going through material, going through magnetic fields and different distances. But these cosmic ray observatories, such as the Auger Cosmic Ray Observatory here on the in South America, near Milagüe, which is about a 8-hour drive south of Mendoza, where is actually in a high altitude plane, and you can see all the charged particles or the proton charged particles as a function of energy. And these are 10 to the 3, 10 to the 6, 10 to the 9. Boy, it came out kind of fuzzy. It's not that fuzzy on mine. Huh. Okay. And so so we can, not only do we have to worry about cosmic radiation when we go into space, or even us living here at different altitudes, or planning for a moon or a Mars mission where people go onto the surface. We could also not only have to worry about that radiation, we could actually use it to do science. So my conclusion is space radiation is very dangerous to living things, and we're lucky because we're nice distance away from the sun where our temperature is cozy, but we have a magnetic field, and our sun has a magnetic field all to protect us. And so we make a nice habitable environment, something that might not be true of other exoplanets. But these cosmic radiation from deep space could also be used to study the universe in new ways, such as high energy gamma rays or charged particle cosmic rays. We on Earth are very protected. Earth's magnetic field, Earth's atmosphere, sun's magnetic field. If you go to Mars, the sun's magnetic field is less. If you go to Venus, by the way, Venus has a very nice magnetic field. It's actually just about the same as ours. And of course, they're closer to the sun, so they're actually have better solar protection. And they have an even thicker atmosphere than ours. It's all sulfuric acid. That's a different problem, but you can always imagine terraforming Venus to make it habitable. If the space ethics lets us do it. Well, it's better than Mars. So anyway, humans traveling in space have to be protected from space radiation. It's very deadly. Going to Mars and the moon, gives us no or very little protection, since the Earth's atmosphere is 1,000th that of Earth and no magnetic field, as well as the moon has no atmosphere and no magnetic field. And any equipment you send into space could easily be destroyed by space radiation if you don't have it properly protected.